So let's start with the problem number 2.246 from Iradov. It says that making use of Poiseuille equation, find the mass mu, of gas flowing per unit of time through the pipe of length L and radius A if constant pressures P1 and P2 are maintained at its ends. So it pretty much looks like a very simple problem on Poiseuille equation, but well, let's start by writing this Poiseuille equation, which says that delta P equals to the most important part of this problem is not just to directly apply Poiseuille equation. The most important part of the problem that it deals with gas, not with liquid. This equation was derived for incompressible liquid. And now we deal with compressible gas. And of course, since the pressures in here and here are different, that means that density of the gas in this part of the pipe are also different. So we need to somehow generalize Poiseuille equation, and after this generalization, this Poiseuille equation should be applicable to gas. Well, let's do it as follows. Let's assume that we study a space between two cross sections inside the pipe, and in between these two cross sections I may assume that the density of my gas hasn't changed by far, well, it changed only slightly. So I can assume that in between these two cross sections the density of the gas is approximately constant. So in this case, I can apply this Poiseuille equation, but instead of delta P and L, I would have dP equal to 8 eta dL times Q over PR to the 4. Okay. And also I assume that the temperature of the gas throughout the whole pipe remains constant. So I assume that T is constant. Also I need to somehow understand how my viscosity changes as a function of pressure. You are not able to do this now, but so let me do this for you. The viscosity will also approximately remain constant. That would be discussed further in our lectures about the molecular origins of the viscosity. So viscosity is constant, temperature is constant. Well, now this Q. Of course, since it's not the liquid anymore, Q is not a constant. What is actually constant throughout all of these cross sections? Well, Q is again dV over dt, the volume of fluid per unit of time. Well, of course, you need to fix that by assuming that actually what is constant is mu. mass per unit of time, or density times Q. So from this equation where I multiply density by Q equals to mu, which is constant throughout all of the cross sections of my pipe, I get that Q equals to mu over rho. And that brings me once again to a very standard problem which I have solved. I don't remember how many times I have solved this problem, but determining the density of the ideal gas as a function of pressure. So let's again write let's again write the equation for the ideal gas, the equation of state. PV equals to nu RT, or equal to m over mu times RT. If I bring the volume to this side, that gives me that pressure equals to density over mu times RT, from which I have that density is equal to mu times, mu is already taken. Mu is the mass per unit of time. So in here to label molar mass, I use capital M. Capital M times pressure over RT. So the density is proportional to the pressure. And now I plug it into this equation and get mu over P capital M, and RT goes to the numerator. Mu RT over PM. Again, I say that mu is dm over dt, the mass of the gas which flows through the pipe per unit of time, while capital M is molar mass. Okay, now we plug everything into this equation, and it gives us that dP over dL equals to 8 eta times Q, which is mu RT over PM and now pi r to the 4. Oops, and now once again, instead of r, I have a. So this is a, this is a, and here is also a. And probably the main reason why the authors have chosen a as the radius of the pipe is that r has already been taken by the universal gas constant. Well, I think this is which makes this part of the seminar and lecture most difficult, because most of the variables in different cases describe the different physical quantities. Capital R can be the radius, and here capital R is the universal gas constant. Mu is not a molar mass, but the mass per unit of time. Well, that makes it a bit confusing. Q has nothing to do with heat. But nonetheless, I think this equation is valid. If I replace R by A, that is valid. P times M times pi times A to the 4. And now we can solve this equation actually. So this is the equation which describes you the pressure distribution along the pipe. And I can solve this equation by variable separation method. Variable separation. I just need to do dP times P equals to 8 eta mu RT over capital M pi A to the 4 times dL. And now I integrate it from the inlet to the outlet of the pipe. So what I get here is P1 squared minus P2 squared over 2. So that's what I get when I integrate P dp equals to 8 eta mu r t over capital M pi a to the 4 L, where capital L is the total length of the pipe. Okay, so that answers, wow, what is this? That answers the question of the problem, but I would like to add the final remark that this equation is actually wrong. And one reason why this equation is wrong is that, well, in the Poiseuille equation, we assume that the total force which acts on the streamline is 0. So our pressure forces, they overcome the viscosity forces, and they fully compensate for viscosity forces. But in here, this is not valid, because when the gas flows into the pipe at a larger pressure, it has lower velocity than when it comes out at a lower pressure. So now it has larger velocity. So because here the density is smaller, and since the density is smaller, we need to pump larger volume per unit of time in order to achieve the equality of mass coming into the pipe and coming out of the pipe. So in here, contrary to the conditions of Hagen-Poiseuille equation, the velocity at the outlet is larger than velocity at the inlet. So that means that you have a momentum difference of mu times, okay, some V effective on the outlet minus V effective on the inlet. Effective, which means that, well, it's somehow proportional to the maximum speed here, but it's not exactly equal to that. So part of the pressure difference applied to the pipe goes to change the momentum of the gas on the inlet and on the outlet. So when the gas comes into the pipe, it has lower momentum than when it comes out of the pipe. So that means that actually the pressure forces are not fully compensated by the viscosity forces. So that's the main difference. So actually from this equation, it may look like as if I can, for example, assume that P2 equals to 0. But when P2 equals to 0, that means that the density also goes to 0, and that means that velocity goes to the infinity. So this equation is applicable only to relatively small pressure changes. Okay. And now the next problem. The problem 1.323. It's from mechanical part of the book. So it says that a cylindrical vessel of height h and base area S is filled with water. An orifice of area small s, which is much less than the capital S, is opened in the bottom of the vessel. Neglecting the viscosity of water, determine how soon all the water will pour out of the vessel. So it is initially it is filled completely with water, but as I pump the small orifice, then this water starts flowing from that orifice. So that means that the amount of liquid remaining inside the vessel would decrease until it disappears completely, so it flows completely from the orifice. So it says that we should neglect the viscosity, so that means that probably we can apply Bernoulli equation, which says that pressure plus rho v squared over 2 plus rho gh should be constant. So in the above and below, I have the same pressure, which is atmospheric pressure, so I can discard the first term from the Bernoulli equation. So what's remaining is that, let's say I have only the level capital H remaining inside my vessel. So my vessel is fully filled with water only on the initial moment of time, but in general case, my vessel is only half filled with the water, or not half filled, but partially filled with water. So I can say that at some moment of time, the level of water in my vessel is capital H. So then I can apply this Bernoulli equation to this point here and some point here. So that would give me rho g capital H and almost no velocity. So since this in here, there would be almost no motion of liquid. That should be equal to approximately rho v squared over 2, where v is the velocity of or the speed of the water which flows through the orifice. And as I have said, according to Bernoulli's equation, this velocity is uniform across the cross-section of orifice. So that gives me this velocity, or this speed, and actually by some coincidence, this speed is actually equal to the speed of the solid body which was thrown from the height of h and the speed acquired under the action of gravitational force. So it's exactly equal to this speed. So now I calculate the volume of liquid leaving the vessel per unit of time. So I need to multiply the speed v by the orifice area s. And from that, I can also relate this to the changes of the level h. Of course, as my liquid flows out of the vessel, my level of liquid remaining inside the vessel changes. So this should be equal to capital S multiplied by minus dH over dt. Minus cause my level decreases, so this derivative is negative. And now I have the differential equation which describes me the evolution of the level of the liquid. dH over dt is minus V times small s over the capital S. So this is minus root of 2gh times ratio of small s to capital S. Small s to capital S. Okay, so now I have again the equation which can be solved by a variable separation method. It is applied in almost every problem I am doing now. So I can write that dh over square root of h equals to square root of 2g times the ratio of small to capital S multiplied by dt. The integration of this gives me something like square root of h multiplied by 2. So if I integrate from the initial to the final condition, that would give me minus 2 square root of small h. And remember please that small h was the height of the vessel. So it's negative because my height actually decreases. So in the initial moment of time it was 2 square root of h. At the final moment of time, when all the liquid has left the vessel, it is equal to 0. So the difference between the final and the initial value is minus 2 square root of small h. And that's the amount of time which is required, t, capital T. Okay, and I also had the minus here. Minus and minus, and then T equals to capital S over small s times 2 square root of small h over square root of 2g. So I have capital over small s times square root of 2h over g, and which turns out to be, so this square root of 2h over g turns out to be the amount of time which is required for this body to fall from this height of small h to the level of Earth. But due to this ratio between the base area of the vessel and the area of the orifice, actually it requires much longer for the liquid to completely empty the vessel. Okay, any questions about this? Oh. Okay, and also please note that according to this equation, velocity or the speed approaches 0 as the level of the liquid decreases. So it makes you wonder that actually that if the level of the liquid is very small, it also leaves the vessel at a very small rate. So, and finally, when the level is approximately equal to 0, then this velocity is also almost 0. But nonetheless, even though that the velocity decreases as a function of the height, it takes a finite amount of time for all of the liquid to leave the vessel. Okay, the next one is uh, 2.42. Wow. Oh, that one is very nice. It's a kind of a difficult problem if you don't know how to solve it, but it becomes somewhat simpler if you know that. Find the rate V with which helium flows out of a thermally insulated vessel into vacuum through a small hole. So I have a vessel. Well, that's actually related to the space stations. So I have a vessel which is filled with gas. That is space station. And recently you have heard the news that a small hole was found in the space station. And due to that small hole, the pressure of gas decreased. And due to the existence of that small hole, one sector of the space station was completely isolated from other sectors before this hole was patched. So now we need to understand the physics of this problem. So when we have this kind of a hole, so we need to calculate the flow rate, V. The temperature is 1000 kelvins, so this is slightly different from the space station. And it's filled with helium, not with oxygen and nitrogen. So again, there is another difference from the space station, but all the other stuff remains the same. Flow rate. Probably we need to calculate the speed of outflow in helium. So I need to assume that actually the speed of the helium inside the vessel, I mean the speed of the flow is 0. Of course, there is thermal motion of the helium molecules, but thermal motion has nothing to do with these speeds which are in the Bernoulli equation, because these speeds are related to the directed, not chaotic motion. They are related to directed motion as of all molecules. So inside V equals to 0. So we need to write the Bernoulli equation, but well, I have already prepared the necessary Bernoulli equation during the lecture, because I have said that Bernoulli equation for liquids doesn't apply to this situation, because we can have temperature changes. We have also the density change. So we need to apply Bernoulli equation in enthalpic form. So molar enthalpy plus mu times V squared over 2 plus mu, okay, there is no gravitation here, so no third term, so this is constant. Well, and I feel like we don't have enough variables to solve this problem. Probably we are missing something like a pressure. Probably this pressure would disappear in the end, but let's say we know the pressure here. Okay, so we need to determine this molar enthalpy. Molar enthalpy is equal to the product of the molar heat capacity at constant pressure by the temperature. So let's say that the initial temperature is 1000 Kelvin, but the final temperature, we don't know the final temperature, so we are going to determine it. So let's say that Cp times T plus nu V squared over 2, so this is the final temperature, equals to Cp times initial temperature T. We don't know the final temperature, but we know that there is no pressure outside the vessel, so probably we can assume that the final temperature is something like approaching 0. So that gives us the limit for the velocity, which is 2 times cpt over nu, which is which is the molar mass of the helium. So now we need to substitute all of these quantities. Cp for helium, the question to everyone. Molar heat capacity of helium at the constant pressure. Okay, if I have heat capacity at the constant volume, then it is 3 over 2R. But for Cp? No, it's gamma, 5 over 3. You made this mistake in your homework where you have assumed gamma equal to 3 over 5. That's wrong. 5 over 3, and for the Cp, it's 5 over 2. Or you can apply Meyer's relation and get 5 over 2R. And from here, gamma is Cp over Cv is 5 over 2R over 3 over 2R, which is 5 over 3. Well, actually it depends on anyone, but I find that it is easier to remember this Cv quantity than gammas, personally. So Cv are easier to remember. Sometimes only gamma is given in the conditions of the problem, but well, then we can do nothing about this. Then we need to determine Cp and Cv from gamma. But in this case, when I study monatomic, diatomic, and 3-atomic gases, it's easier to remember Cv. Because Cv for single atomic gas is 3 over 2. For diatomic gas is 5 over 2. For 3 and more atomic gas is 3R. So it changes in this very convenient steps. And if you want to determine Cp, you just add another R to this Cv and get Cp. Okay, so Cp is 5 over 2R times 1000 Kelvin. So, okay, R is 8.31 times 1000 and divided by molar mass of helium, which is 4 grams, or not 4, actually 4 grams per mole. So 4 times 10 to the minus 3, where 10 to the minus 3 comes from the unit conversion, from grams to kilograms. And in the end here, I have 5 times 8.31, so that would give me 41.5. 41.5 over 4, that would give me approximately 10.1. So square root of 10.1 times 1000. So that would give me approximately 3.5. So that means that the outflow speed of helium would be approximately equal to 3.5 thousandths of meters per second. Thousands of meters per second. Well, which is quite large, actually. I actually dream about moving from university to my home at this speed. Sometimes. That's at times when I cannot dream about infinitely fast motion, about teleportation. I know teleportation is physically impossible, but this one is physically possible, but so at least. Nevertheless, in Moscow it's impossible, even with much lesser speed. Okay, so the next one is 1.3 and 31. Okay. A thin horizontal disk of radius r of 10 centimeters is located within a cylindrical cavity. So a disk is located in the cylindrical cavity. This is the disk. That's a cavity. Filled with oil whose viscosity eta is 0.08 P. P is Poisson, a unit for viscosity in CGS system. So I can say that this is a CGS units. Poisson. The clearance between the disk and the horizontal planes of the cavity is equal to 1 millimeter. So there is 1 millimeter of separation between the disk here and the disk here. 1 millimeter. So it looks like quite an engineering problem. So you have some kind of a moving part of the engine, and to prevent the friction between the engine and this cavity is filled with the oil, which actually allows you to maintain this separation. So that's the main reason why the oil is added here. Well, without oil, mostly, if there is some sort of a friction, without oil, that will produce overheating of the moving parts of the engine, and which would eventually lead to the breakdown of the engine. Okay, so we need to calculate the power developed by the viscous forces acting on the disk when it rotates with the angular velocity of 60 radians per second. 60 radians per second. The end effects are to be neglected. Well, since the disk is rotating, okay, I have an asymmetric image here, but please believe me that this is the axis of this disk. So due to the motion of the disk, so there is the disk is a moving part, while the vessel is at rest. So that means that any moving part of the disk and unmoving part of this cavity, they form a condition which was discussed during the lecture, of coed flow. So when I have one plane which moves at some velocity while the other one which is kept at rest, and there is also a liquid in between two of them, so that means that these velocities of liquid have this kind of a profile in between the resting part and the moving part. But of course, different parts of the disk move at different velocities, so that means that the shear stress produced by the viscosity is different at different parts of the cylinder. So let's assume that this velocity is equal to V, and then the shear stress would be equal to the product of the viscosity coefficient by the derivative of the velocity over the normal direction. So here goes the normal to this plane. So that means that this is eta times V over H, where H is the separation or clearance in between the disk and between the cavity. Okay, this velocity is actually proportional to the distance from the axis of the disk, because the disk rotates at the constant angular velocity omega. So I can calculate V as the product of omega and the distance to the axis r. So that is the shear stress, and we need to calculate the power developed to overcome all of these viscosity forces or drag forces. Okay, as you see, we have something which is dependent on the radius, so that means that in order to calculate this final power, we need to perform some integration. What we need to integrate? We need to integrate the drag force, which is the product of T times the element of area of the disk. So tau times the element of the area. And also, since this is the power which we are dealing with, we need to multiply the drag force by the speed of the corresponding element. So I need to multiply tau dA by the speed of that element. So all in all, that gives me twice the integral from 0 to capital R. Twice because I have two surfaces, the top surface here and the bottom surface here. And everywhere on the top and the bottom force I have a drag. So that accounts for the top and bottom surfaces. And for the multiplication, I have that eta times omega r over h, and multiplied by velocity, which is once again omega r, and multiplied by the element of surface. And the element of surface is, well, now I can write like 2 pi r times dr. So that's the element of surface. I consider a fully circular element of surface because all of this depends on the r. It doesn't depend on the direction on which you go from the axis. So that means that in this case I can take the circular elements of surface, which are located at the same distance from the axis. So now I have this integral, and now I just need to calculate it. First, I take out of the integral all of the constants, like eta, like omega squared, like this pi. Okay. I can even take out 2 pi. 2 eta omega squared 2 pi over h, and the integral from 0 to capital R of r cubed dr. This kind of an integral easily gives you r to the 4 over 4. And this 4 coincidentally allows you to eliminate these two factors of 2. So in the end I have eta pi omega squared r to the 4 over h. I hope I haven't messed everywhere during this derivation. I see actually no place where I can do a mistake here. Okay, so now I need to perform the calculation. Okay, let's do this in CGS units, since I already have the viscosity in CGS units. So 0.08 times pi times omega squared, which is 3,600 times radius to the 4, which is 10 to the 4 over h, where h is 0.1 centimeter. This is 1 millimeter, so that means that this is 0.1 centimeter. Oh, that's quite a large quantity actually. So 10 to the 4, 10 to the 4, but here 10 to the minus 2. So that would give you 10 to the 6 times 8 pi times 3.6. Okay, let's do a rough calculation of this. So 3.14 times 3.6 would give you something like, okay, if I multiply this by 3, that would give me 10.8. 10.8 plus 0.4, so this is 11.2 approximately. 11.2, but once again I need to multiply this by 8, so that would give me, if I multiply 11.2 by 8, that's approximately, let's say, 90. So this is 9 times 10 to the 7 of CGS units of power. Okay, what would be CGS units of power? Energy is measured in erg. Power is measured by energy over the second, so erg per second. Well, if I want to convert it into SI units, I need to remember that 1 erg is probably 10 to the minus 7 of joule. Let me show this. 1 erg is the product of 1 din by 1 centimeter. 1 din is the product of 1 gram per unit of acceleration, which is centimeter per second squared, multiplied again by 1 centimeter. So this is 1 gram centimeter squared over second squared. So if I convert it into SI units, I need to convert grams into kilograms, which gives me 10 to the minus 3 of kilograms. For the centimeters, I get 10 to the minus 2 meters squared over second squared. So that gives me 10 to the minus 3 kilogram, okay, by 10 to the minus 4 meters squared over second squared. So this is 10 to the minus 7 of kilogram times meter squared over second squared, which is 10 to the minus 7 joules. So that means that actually I spend 9 watts per second approximately to overcome all of the viscosity drag. E equals to 9 watts. That's approximate. Well, it turns out that actually I got the answer correctly. Okay, well, we have solved all of the problems. Let's look probably through zero-level problems. They should be somewhat simpler than what I have solved already. Zero-level problems are 16, 17, and 19. Well, the problem number 16 is pretty good. I would like to solve it, actually. So I have a vessel of a certain height h, and I pump a hole in this vessel, and this vessel is fully filled with water. I pump a hole, and then water comes out of this vessel, but due to the gravitation force, this flow of water meets the ground at some distance L from the vessel. So I need to calculate the optimal altitude of the hole, which allows me to reach farther away from the vessel, farthest point away from the vessel. So what's the difficulty? If I pump the hole too high, then the velocity of the liquid would be too small, and then it would drop near the vessel. If I pump the hole too low, then, well, the velocity would be large, but it would take me so small time to get to the ground that my water would not travel too far away from my vessel. So all in all, I have two factors which are in competition with each other. So let's assume that I have pumped a hole at the elevation of small h. So according to the Bernoulli equation, then I need to write that rho g capital H equals to rho v squared over 2 plus rho g small h, from which I can determine the speed of the outflow, which is 2g times capital H minus small h. So as you see that if I pump the hole too high, so this difference becomes very small, and the velocity also is very small. And now I need to calculate the distance traveled by the water. I assume that when this water travels, it does so independently from other parts. So it can be considered like the motion of the object thrown like with your hand. So then I can write that if I choose this frame of reference here, I can write the law of motion. First of all, x coordinate would change proportionally to the time of travel t, while y coordinate would be equal to h minus gt squared over 2. So it takes the amount of time t equal to square root of 2h over g to reach the ground, and that means that the distance traveled would be equal to v times t, that is v by square root of 2h over g. And now I substitute this for v. And actually g is eliminated from my equation. So that means that if I bring my vessel from the Earth to the surface of Mars, the answer would remain the same. So here I have 2 square roots of h times capital H minus small h. Okay, and how to find the optimal value of small h from this equation? Any ideas? Derivative. One of them is take the derivative. Okay, what's your idea? Huh? Derivative too, yes? Derivative. Okay, any other ideas except for derivative? It can be done without the derivative. Well, actually, what it says here that you have some kind of a quadratic trinomial under the square root, the quadratic function of h. As you know, all of the quadratic functions are, well, they produce these parabolas. So I can plot like the plot of this function under the square root as h. So since I have h minus h squared, so that means that my parabola crosses this horizontal axis at h equal to 0. So if I take h equal to 0, that would give me 0. And if I take h equal to capital H, that would give me 0 too. So in between these 2 points, I have this parabola, and I need to find where the vertex of parabola is. And since the parabola has symmetric shape, that means that my vertex is located at h over 2. So I can do this even without the derivative. So the end is, I have the answer 2 multiplied by h over 2, which is h. Well, quite a coincidence again, that the maximum distance traveled from this vessel will be exactly equal to the height of this vessel. And there is another way to do this calculation. It's called Cauchy inequality. It's one of the fundamental inequalities in mathematics, and it says that in the general case, if you have so a certain number of quantities which are larger than 0, a2, a1, n3, and so on and so forth till an. And if you have n variables larger than 0, then a1 plus a2 plus a3 plus and so on and so forth plus an over n is greater or equal than the root of n's power of the product a1, a2, a3, and so on and so forth to an. So this is called geometric average, this is called arithmetic average. So the Cauchy inequality says that for any number of numbers, real numbers, positive numbers, the arithmetic average is greater than geometric average. In the case of the 2, it has a very simple proof. So let's say if I have a1 plus a2 over 2, it should be greater or equal than square root of a1, a2. And it can be proven directly. a1 minus 2 square root a1, a2 plus a2 should be greater or equal than 0. And that is indeed correct, since the left-hand side is the full square. Square root of a1 minus square root of a2 squared. And indeed, it's obvious. A full square of some number is always greater than or equal than 0. There is also a condition for this inequality which immediately follows. The condition when this inequality becomes an equality. That is when square root of a1 equals to square root of a2, so that a1 equals to a2. In the general case, again, this inequality becomes an equality when all of these numbers are equal. And you can check it yourself. So if every number is equal to the same number a, then the arithmetic average would become equal to a, and this geometric average again would become equal to a. Indeed. Well, in here I can write, so this is the geometric average of h and capital H minus h. So according to this inequality, that should be less or equal than 2 multiplied by h plus h minus h over 2, which is again h. And the condition for this to be an equality is that h equals to capital H minus h, which gives you once again that small h should be equal to capital H over 2. So sometimes there exists multiple ways to solve the optimization problem. So you don't always need to do this derivative, but derivative actually is the most reliable way, which is applicable to the most general cases. But sometimes, well, you can work around without a derivative. And thank you for the attention. I think with this I can conclude my seminar. If you have any questions, please feel free to ask them.